What? Okay, so we've got two functions here, f and g. I'm going to see what happens when I plug 5 into the f function, and then I'm going to take the result and plug it into g. Okay, so f of 5 is what? 13. Okay, so I do 3 times 5 is 15, minus 2 is 13. And then if I take that 13, the result from what I got from f, the output from f, and put that into the g function, g of 13 is 5. Yep, because you do 13 plus 2 is 15, over 3 is 5. So it's like we got a round trip, right? It's like my two machines. You put in an input, f does some stuff to it. You take that output from f, put it into g, and g undoes everything that f did. And you get your 5 back. So you put a 5 in, and you get your 5 back. So let's see what happens if I compose them in general. So it worked with 5. With a one specific example of 5, we got a round trip. Let's see what happens if we do it with a generic x. So we're going to plug into f first. Remember, this means g of f of x. So in the last example, we would have plugged x into f, or 5 into f. But we don't have a specific x, so I'm going to replace f with its formula. So this becomes g of 3x minus 2. Okay, so I just made a substitution, replacing f of x with what it equals. And then this means in the g function, I'm going to replace all the x's with 3x minus 2's. Okay, so instead of x plus 2 over 3, it's going to be 3x minus 2 plus 2 over 3. It is, yes. Yep, we're just doing composition to start. All right, so 3x minus 2 plus 2 over 3. Well, minus 2 plus 2 is 0. So this becomes 3x over 3, which is x. So we got a round trip, right? We saw that when we plug an x in, you get an x out. So if I drew a picture of this with the function machines, f is my first function, g is my second. I put an x in, I got f of x out. I took that f of x and put it into g, and out came x again. It's a good question. But yes, it definitely has to do with what the two equations were. Yeah. Any two f and g won't necessarily undo each other. Yeah. These two equations are special. So whatever f does, it seems whatever this f machine does to its inputs, g undoes it. Okay, so you put something into f and it does some magical things, turns it into an output. You take that output and put it into g, and it magically changes it back into the x we started with. Okay, so let's see if we can reverse the order of the machines. Have x go into g first and then into f. F of g of x. See if we can get a round trip this way. So now replace g of x with its formula, and I get f of x plus 2 over 3. So that means in my formula for f, I'm going to replace all the x's with x plus 2 over 3. So instead of 3x minus 2, it's going to be 3 times x plus 2 over 3 minus 2. And when I simplify this, the 3's cancel. Then you have x plus 2 minus 2, which is x. So I get a round trip this way also. I can change the order of the machines. I can put x into g first, take the result and put it into f, So when I plug x into g, out comes g of x. Take that output and put it into f, and f undoes whatever g did because I get the x back. Yes. There is, yes. These two kinds of functions that have this special property where one undoes the other, or you get a round trip when you compose them, are called inverse functions. Two functions that undo each other like this are called inverse functions. That's a good question. What's the point? So it's kind of like a reverse lookup. Like think of a database with names and phone numbers. Okay. So we have one function where you can type in someone's name and up pops their phone number, right? That's really helpful. But another helpful function would be as if you could type in the phone number and up pops their name, right? So one function, so those two functions are inverses of each other. So it's just, they talk about, both functions deal in the same information. It's just a matter of rearranging what's the input and what's the output. So we said they were the two, when you compose two functions that are inverses, you get x. And our notation for an inverse function, if g is the inverse of f, we write g is f, and then we put, like, it looks like an exponent to the -1, but it does not mean to the -1. We're repurposing an old notation, and you would just read that as f inverse. No. It's related to multiplicative inverse. So I'll do a quick aside here. Like, what do you multiply 5 by to get 1? 1/5, right? So this is called, these two numbers are called multiplicative inverses, numbers that you multiply together to get 1. So 1/5 is the same thing as 5 to the -1. So they're using this notation from multiplicative inverse and applying it to functions. But in this case, it does not mean 1 over f. All right, so what is the inverse of putting on your socks and then putting on your shoes? Yeah, take off your shoes, then take off your socks. So inverse functions completely undo each other. So if my function was put on my socks, put on my shoes, the only way to undo it is to take off my shoes, then take off my socks. Right? So we always undo things in the reverse order that we did them. It's kind of like watching Rewind. You know, so you do some stuff and then rewind it and go backwards to undo it. So what would the inverse be if you add 3 to x and then you multiply the result by 6? How would you undo adding 3 and multiplying the result by 6? You got it. Divide by 6 and subtract 3. So you have to find what operation should I use to undo what was done, and in what order should I do it? Do it in the reverse order. Okay, so first I added 3, then multiplied by 6. So to undo, divide by 6, then subtract 3. Reverse the order and change the operation to the opposite. All right, so let's make a table for f inverse. Okay, we have a table of values for f, some inputs and some outputs. I want to make a new table that has inputs and outputs for f inverse. Okay, so remember that the function and its inverse make a round trip. So think of it as two successive function machines. So if I put a 1 into the F machine, I get an output of 2. That means that if I put a 2 into the F inverse machine, what should my output be? 1. Yep, it should just undo what was done by F. Okay, so if I put a 2 into the F machine and get a 5, that means if I put a 5 into the inverse machine, I should get a 2. 3 becomes 7. 7 goes back to 3. 4 turns into 4, and 4 turns back to 4. 5 turns into a 1. That's what F does to it, right? 5 becomes a 1. That means F inverse, 1 becomes a 5. Yes. What's that?
We have functions that have different numbers, but they'll have 3 different numbers.
Yes.
So that means some.
Yes, that is a fantastic observation. So one of the things that we talked about with functions is that the definition of a function is that each input has to have exactly one output, but it was okay to have more than one input go to the same output. When you reverse it, if this was, say, a 2 right here, if that was a 2 also, 1 to 2 and 5 goes to 2, that's okay, that's a function. But when I reverse it, now I'm going to have two inputs going to, one input going to two different outputs, which is not allowed. So this guy would not be a function. Yeah. Not all functions have inverses, exactly. Yep. That's part of the lecture. We're going to write it down. That's okay. All right, so what you notice about these two tables is that the rows just swapped, right? The input row for F became the output row for F inverse, and the output row for F became the input row for F inverse. So that means that the domain of a function F is the range of the inverse function, and the range of F is the domain of F inverse. So inverse functions just swap the role of input and output, meaning the domain and range switch. All right, so not all functions have an inverse function. So let's fill in the table of values for the absolute value of x. So absolute value of -2 is 2, 1, 0, 1, 2. All right, so this is my absolute value of x table. Now I'm going to try to create a table for the inverse function of the absolute value of x. So I just do my round trip thing. So -2 becomes 2 when put in the F machine. It means that 2 becomes -2 when it goes into F inverse. Just make the round trip. -1 becomes 1. 1 goes back to -1. 0, 0, 1, 1, 2, 2. Okay. So now we see the problem that Catherine foresaw coming, right? I now have one input, 2, right? The number 2 is a single input that's producing two different outputs. Sometimes you get -2, sometimes you get +2. That means that this guy is not a function. Yep, every other number. Yep, 1. Yeah. It only takes one, though. It only takes one instance where a single input has two different outputs, and you declare the whole thing not a function. So you only have to circle one to show that it's not a function. So graphically, let's think about the problem here. If I plot my points for F inverse that I drew here, I would have 2, -2, 1, -1, 0, 0, 1, 1, 2, 2, and I get this guy. Maybe now it's easier to see. Right? Rather than looking at it in table form, now we look at it graphed and we go, oh, clearly doesn't pass the vertical line test. How do I know it continues? That's the inverse that I drew. Yeah. So I take a quick glance at this inverse and I go, oh, doesn't pass the vertical line test. It's not a function. So graphically, I could have imagined what would happen when I redrew it, when I redrew the inverse and saw that it didn't pass the vertical line test. And you can see it before even drawing by doing a horizontal line test. Because I have inputs, -8 and 8, say, that give the exact same output. So when I switch the role of output and input, now it's not going to be a function.
So basically, any graph that is like asymmetric.
Yep. Yeah. Any graph that has y-axis symmetry would certainly not have an inverse function. Yeah. But those aren't the only kinds. So graphically, we use the horizontal line test to decide if a function has an inverse. If every horizontal line intersects the graph at most once, then it has an inverse function. So we're a little bit sloppy with the word does not have an inverse, with the phrase does not have an inverse. Every function has an inverse. It's just that its inverse is not always a function itself. Okay, so every function has an inverse, but its inverse is not always a function. And we do often say f doesn't have an inverse. If it doesn't pass the horizontal line test, it doesn't have an inverse. But that's only because this class is about functions. And if the inverse isn't a function, we don't even care about it, right? So, so just know that when they say it does not have an inverse, it means that its inverse is not a function. So let's draw a picture of a function that is always increasing. That means that as I read it from left to right, it's always climbing uphill. So any function that's always going uphill, like that. Would this pass the horizontal line test? It would. So what can you say about a function that's always increasing? It always has an inverse function. Yeah. All right, so a function whose inverse is also a function, or shorthand, a function that has an inverse. We call that kind of function a one-to-one function because the outputs and the inputs correspond in a one-to-one way. Each input has exactly one output, and each output came from exactly one input. So the problem with absolute value is that I don't have that one-to-one correspondence. I have -2 and 2. F sends both of them to the number 2. In a one-to-one function, you can only have one arrow going in either direction. So, like you asked a couple minutes ago, Ayana, what do we use this for? It's important to be able to understand what an inverse function represents when you're using a function to represent a real-world thing. So for my first example here, we have a function, f of t, that gives the population of Greenfield as a function of time, t, in years since 1990. Okay, so what are the inputs into this function? Not talking about inverses or anything yet, just interpreting this function. What are the inputs? What goes into the function machine? Years. Oops, 1900, not 1990. Okay, and what are the outputs? Population measured in number of people. Okay, so suppose I told you that F inverse of 1400 equals 57. I would like to explain what this means. So this 1400 in parentheses here, that 1400 is an input to F inverse, right? It's being plugged in to the inverse function. That means it was an output from the function F. So that 14, what does it represent, the 1400? A population. And the 57, that's an output from F inverse, which means it was an input from F. So that 57 represents 1957. So this says the population of Greenfield was 1,400 people in 1957. I don't know, probably. So I'm making a big assumption by using F in that this F has an inverse function, right? What is that assumption? That the population is always increasing. Or always decreasing, yeah. Yeah. We're assuming that the population hasn't oscillated at all, right? Either it's always increasing, which is more likely, right? Or always decreasing. So yeah. No, not always. No, when you're using an inverse, you have to, here we are assuming that the function is one-to-one, that for each year there is a unique population, right? That the population didn't hit 1,400 again sometime, you know, in the 60s or something. It could not be the same for a little while, because if I drew function that increases and then is the same and then increases, right here, I wouldn't pass the horizontal line test. All right, so the inverse function in general, so kind of like I gave a little sentence explaining what F does, right? F gives you population as a function of time. F inverse gives you time as a function of population. F inverse gives time, that is a year, as a function of population. So like I said, it's like a reverse lookup. F is the function where you can type in a year and up pops the population, if it was a database on a computer. And F inverse is the reverse lookup, where you can type in a population size, and F inverse tells you what year Greenfield had that population. All right, so in your groups, I want you to do B and C. So let's discuss. C equals F of Q gives cost as a function of the number of lunch boxes. So this is a helpful, handy little trick, is to be able to read the notation like an English sentence. This says cost is a function of Q, right? C is a function of Q. So that The of part, a function of, that's your input. Okay, so Q is my input, and Q represents number of lunch boxes, right? So my input is number of lunch boxes, and my output for this function is cost. Cost to manufacture that many lunch boxes in dollars. So if I write F inverse of 200 equals 40, the number in parentheses 200 is an input into F inverse. That means take 200 and plug it in, apply rule F inverse. Okay, so it's an input to F inverse, which means it was an output from F. So that 200 is a cost in dollars. And the 40, it's an output from F inverse, means it was an input from F, so it represents number of lunch boxes. So this sentence says that for $200, you can produce 40 lunch boxes. And in general, the inverse function tells you, for a given cost, how many lunch boxes you can make. It tells you number of lunch boxes for a given cost. You plug in cost, you get out number of lunch boxes. Okay? All right. So if t equals f of v gives time to drive to New York City at a velocity of v miles per hour, this says time is a function of velocity. Time is a function of velocity. Read it as a sentence. So my inputs are the thing in parentheses, right? Function of velocity. My input is velocity. And we'll measure that in miles per hour. And then my output would be what? Time in hours. Good. Okay, so if F inverse of 3 is 65, this 3 is an input into F inverse, which means it's an output from F, so that's a time. So to get to New York City in 3 hours, I have to drive 65 miles per hour. No, I don't have any equations right now. We're just, yeah, there may be an equation, and when you plug 3 into it, you get 65. Or it might just be a table of values. So to arrive in 3 hours, drive 65 miles per hour. So in general, F inverse tells you how fast to drive given a certain time constraint. So you input time, and F inverse outputs necessary speed. Okay? All right, so next thing, I'm going to have you work in your groups on this activity called columns and cell phones. Kind of a fun one.